So, all right, I think I'll need to share my screen, right?
Yeah, let me, I think I need to give you permission.
Wow, I can share my screen now.
All right, cool. Share my screen. Cool. All right, so this is good, right?
Mhm.
All right, cool. So we'll talk about uncertainty and information. So basically, a lot of information theory is based on like this concept of trying to extract the most amount of information that you can possibly get, to where the information is, or the like knowledge is actually information that is modeled to be useful. So you need information to be able to get knowledge, and so we'll explain more what that actually means going down. But just know that information is not actually equal to knowledge. Cool. So here they have an example of uncertainty and information. So here you see like two graphs or whatever, where you see like 25% rainy, 75% sunny, and then you have a 50-50 between rainy and sunny. So which day would be uncertain? Obviously, it would probably be the first or the second day, right? You have a
Mhm.
50-50 chance of it being rainy or sunny, so you don't really know. So how do we quantify uncertainty? Uncertainty is kind of like entropy. So here it says like high entropy is correlating to high information, um, which I think might actually be incorrect. High entropy should be correlating to low information because, well, okay, you'll see down here. So
Okay.
um, so here it's talking about a random variable x, and then you have a probability distribution of p. So this is just like the basic formula for calculating information, for at least discrete, like, or some probability distribution, right? So basically, like, all information will be written in bits. So this is just telling you, like, okay, if I have a 100,000 word vocabulary or dictionary, the odds of me selecting a random word is 1 out of 1,000, 100,000, right?
Mhm.
So the information I could get on average, or the information that I would get from any given word is about 16.6 bits. Um, so here's a couple more examples of like information. Uh, so 1,000 word document, get more information. So like basically, the smaller your sample size is, the more information that you'll actually get per sample.
I see.
Yeah,
Say that sentence again.
yeah. So the smaller your like event space is or your sample size is, the more information you'll end up getting per sample. Um, so which makes a lot of sense, right? Like you would know more about future inference of events for a sample space of 1 to 5 of like coin flips than say a 1 out of 100,000, like 100,000 word vocabulary, right? I can say with more certainty that the next coin flip I want to the next probability of events that uh, or the next probability of an event falling in this event space would more likely follow this distribution, right? So I'll actually have more information about that than I would if I had to pick, one random word from a dictionary of 100,000. There's
Oh,
more possibilities, so I get less information on average from each of these events.
I see. And then can you go back to information versus knowledge?
Yeah, yeah, yeah.
So I just want to make sure I understand.
Right. So basically, information is just the data. So information would just be your like event space. So like if I have a data set of events I've observed, you have information. But knowledge is actually like information that's modeled to be useful. So basically, like you would need to figure out a distribution or figure out a model that takes that data and then produces some useful, just like some useful like model so that you can then make predictions.
I see.
The model basically turns that information into something useful,
Okay, and that's knowledge.
and that's knowledge, right? Yeah, I don't think it comes up that much, but for like a conceptual understanding, that's helpful. Here's a little bit about compression. So compression is just like, I mean, so we know what compression is, but here we talk like they give examples of a sequence of different events, right? So you have coin tosses, words in a language, notes, and you always want to record the sequence of events in the smallest possible space, because I was like just like I was alluding to earlier. The more that you can constrain your event space to be the smallest representation of all possible events or all of your calculated events, the more information you'll be able to pull from that. Um,
The more information, the more knowledge.
the more information. The
Okay.
knowledge aspect of it comes from the fact that you're able to determine a model or a distribution that it follows, so that if there are additional events in the future, you'll have a lot of information from that, right? You'll gain a lot of knowledge from that,
Okay, I see.
right? Your event space is like your data is just it's just information.
So should we think of information as so like high information being when you basically have like each thing you see gives you a lot more certainty.
Yeah,
Okay.
exactly. And
And you've sort of like maximized the things per certainty ratio kind of thing.
yeah.
I see.
So okay, so then you want to basically record the like the sequence of events in the smallest possible space. You want the shortest representation that preserves all the information. So it would be your most efficient manner of, uh, or your most high information manner of representing all of your events. And so now it's asking you like how much information does a sequence of events actually contain? So we'll look at this example of 5 coin tosses, right? So they're talking about encoding each of your events in a certain in different types of encoding metrics. But if you look at it, so here they have heads is 0, tails is 00, right? Well, tails is happening 4 out of 5 of these events. And so what that means is for this encoding approach, you would have a total of 9 characters, or here, well, you have here's like each number is a character. So you're taking 9 characters to represent 5 events. So it asks like, okay, so which one has the higher probability?
Tails.
Right. And then which one should carry more information?
Heads.
Heads.
Exactly. So that means that our encoding scheme is not actually very good.
Right.
It's not very efficient. You get more information out of the fact that there's 1 heads out of your whole event space than knowing that there's 4 tails. And we'll expand more on that idea a little bit further down. So here's another approach. Here we have the same exact distribution of events. You have 4 tails, 1 heads. Here you do heads is 00 and tails is 0. This only takes 6 characters to represent, and now we have a more optimal, like a more efficient encoding scheme that prioritizes high information as opposed to, I guess, yeah, just prioritizes high information.
Would it be high knowledge?
It could be. It could be. So, like I was saying, the thing about knowledge specifically is you being able to figure out a model to make sense of the information. Information will only become, so this, you can derive a model from your data set. So we'll talk about like cluster like the evaluation stuff, which is all about like mapping your ordered data into probability distributions. So if your event is P, or if your whole event space is P, you may find a distribution Q, and you'll look at how those two correlate to each other. This is kind of similar. So when your evaluation for that concept of mapping of all your data P to a model Q or a distribution Q, when those things are in or I guess when the error or like the evaluation metrics, whatever you choose, is really high or really low, um, then you're starting to get really good knowledge out of your data, right? Um, cool. So what they're saying here is basically that your frequently occurring events you would want to have with the smallest encoding representations as possible, mainly because they happen in high frequencies, right? So you would basically be increasing the amount of bits that it would take to represent all of your data by providing higher, or by not having the smallest possible encoding for very frequent events. Not to mention, very frequently occurring events don't really provide high information, um, mainly because they're, uh, I guess, high frequency events are technically things that occur near the mean of a distribution, right? So that would mean that there's high variance in in those samples. Yeah, so we want to maximize the information per character. So it's the most uncommon events that happen that provide a lot of information, and not the common events. It's kind of like at first it was kind of unintuitive. Like it took a little bit to understand like how things that happen at the very lowest, like the furthest sigmas away from a distribution, tend to tell you the most information. But when you think about entropy, uh, this all makes a lot more sense. Okay, so here's a little bit of background theory about Shannon's the guy who made up information theory, or started asking the questions um, about encoding. So h of x of y is entropy, and so we'll talk about entropy in a sec. Okay, so here's kind of where it all gets somewhat interesting. So entropy is basically the expected number of bits needed to encode a randomly drawn variable of y under your most efficient code. So it assumes everything is efficiently mapped. But what you're doing is you're taking the probability of uh, your event y, and then times the log of p of y. Yeah, okay, so let's see. Yeah, okay. So the most efficient code assigns negative log of 2. So you're always subtracting entropy from your individual probabilities. And the examples really make a lot of sense. We'll look at the examples down below. And it helps like make this concept of entropy a lot more concrete in the balance between entropy and actual information.
Uh,
Yeah.
is it subtracting? What do you mean by subtracting entropy?
Yeah. So every like random
Are we summing these together or something?
yeah, we're summing the negative log, like the negative is the negative
Oh,
sum
okay.
of
Okay, so you
everything.
always okay. Then the number will always be negative.
Yeah.
The entropy
Well,
will
okay.
always be negative.
No, it won't always be negative. It can't be negative. Like the you'll see down below, but like there's rules, there are properties of entropy where the entropy of a system can never be less than or equal to 0. Or
Okay.
it's always greater than or equal to 0. There's always entropy in every system. So you'll see how the math works out, but the negative has to do more with the fact that it's log base 2. Yeah,
Which you can pull in, and so then it's just 1 over py.
yes.
Log 2, 1 over py. Okay.
Yeah.
Okay, so here is so this example goes into discrete random variables. So we'll look at a sample of a sample space of coin flips, and they've denoted p plus as proportion of heads in S, and then p minus is the probability of tails, and then entropy is the uncertainty. So it's approximately equal to like I was saying earlier, it's negative p of the negative probability of getting heads times the log base 2 of the probability of heads, and then minus the probability of rolling tails, log base 2 of tails, or the probability of tails. So
Okay. I
so
think I
like
see
I
what
was
that
saying,
means.
entropy is all about randomness, right? It's like well, I guess in this case we're talking about uncertainty. So in an event space where you have six rolls, or 6 coin flips and they all were tails, that's a really, really unlikely scenario, correct? So, however, it's unlikely, but you have a high certainty about what your next possible event would be. It's very, very likely that the next thing you roll would be a 6, or it would be a tails, right? So you have the probability of heads, it's 0 out of 6, and then the probability of tails is 6 out of 6. So the entropy of this specific event set is 0. There's no uncertainty about the values. Does that make sense?
Mm-hmm.
Yeah.
Okay, so based on just the way the system is performing, there's a good chance we feel pretty certain how it's going to perform in the future.
Right. So
Tails.
it's kind of like you don't know anything about the coin, right? You don't know if it's it's a fair coin. You don't know if it's a weighted coin or
No,
biased coin in any way. So you don't know anything about the system other than the spread of samples.
I see.
So by seeing something like this, a 0 out of 6, or 0 for heads, and all 6 coins all 6 tail or coin flips for tails, this
Okay.
gives you a really high intuition or a lot of information basically about what your next possible coin flip may be, and
Yeah.
it's very likely that it would be tails. And
Okay.
the other thing is that this says that there's very little entropy in that system, and there is very high information. This is a very unlikely event. So if you were to imagine this as like a probability distribution, uh, this would be something at the very tail end of a sigma. There'd be several sigmas away from the mean, right?
Yep.
It's so unlikely. And then yeah, okay. So now we have another event sample where you have 1 heads and 5 tails. Now you're looking at the probability of getting heads, negative 1/6 log of 1/6 minus 5/6 log of 1/6. And so here you get entropy. So you can see like how the more you start, the
Wait,
more,
why is it still log of 1/6 on the second one?
oh, I think that's a typo.
Okay.
Yeah, it's a typo.
Okay.
Because that should be the probability of tails. It should be 5/6. But I think the math is correct. I think it
Okay.
should still be 6.65. But you see how entropy is growing as the sample, the number of heads and the number of tails become equal. So you'd imagine that if your heads were 3 and tails were 3, you'd be at 1. The entropy of that system would be 1. It's really uncertain what your next event would be, whether it would fall in heads or tails, and there's a very little information in that system.
Does that mean that we're never going to have an entropy higher than 1?
Exactly. You can't have an entropy higher than 1.
Okay.
So here are the probabilities of entropy.
So 1 is the most uncertain.
I think so. I don't think I've seen any examples where the entropy of the system goes higher than 1.
Okay. But if you get yeah, it doesn't. Yeah, I feel like it doesn't make sense because these are all fractions. So.
Yeah.
Oh, but you know what? If there's more than 2, maybe that's possible.
No, but they're all fractions from the same set, right? So like,
Yeah, these are all fractions from the same set.
got to sum to 1.
Okay.
Right. So the properties of entropy for at least discrete random variables, you're just taking the sum of the probability of that category or that event, and then the log of 1 over the probability of that event. So like I was saying earlier, all entropy has to be greater than 0. That's just a natural rule of all systems across nature just have entropy inherently. And so all entropy will be non-negative. At the very least, it could be 0, where you know there is, you have a very unlikely set of events, like 0 out of 6 being heads. Entropy is invariant, so if you have like, this is just saying that it doesn't depend on all of the other events in the system. Each event has its own entropy. And then here we're talking about probability distribution, and this relates really well to the cluster evaluation stuff. If you are attempting to take a data set of P data points, and you want to find a distribution, some other distribution for it, like Q, so you translate it to distribution Q. that translation always has more entropy than the original data set. So it'll make a little bit more sense when you look at like ground truth labels and then the predicted probability distribution. So we'll talk about that in cluster evaluation. But so does that make sense that like
the entropy will always be higher?
Your sound went weird. No, sir.
Oh, okay. One. Can you hear me now?
Yeah.
Okay. I was asking, how does Q relate to P?
Yeah. So so like P is just a data set. So like say I have say I have like 10 coin flips. And I just have a discrete set of data. So like I have 10 coins and I have the outcomes of those 10 coins.
Mm-hmm.
And in the I want to put it in some sort of distribution that lets me predict what future events or make inferences about what future events would be. So I just make an assumption that, okay, I'm going to assume that Q is a Gaussian distribution, or I'm going to guess that this is a normal distribution, like a Gaussian or a Bernoulli or something different, right? That's not just the discrete set of events. So what you're doing is you're taking the probability of the event in the original untouched data set, and you're taking that probability and multiplying it by 1 over Q, which is now the translated data, like the translated distribution. So that's saying like, what are the odds of me getting heads if this was a Bernoulli distribution? So that's what Q would represent. But you're taking the same probability from the original untouched set. You're making an assumption, and then you're seeing that we'll figure out, we'll talk about how well that actually maps, like how good is my distribution, like my random selection for this distribution of data. That's more on the evaluation side. But this is just telling you that anytime you take the untouched observations of your data set and then apply it to some distribution, your original set will have less entropy just inherently than when you translate it to some other distribution.
Thank you.
Yeah. And that makes sense, right? Like you observed a set of events, a discrete set of events, and you've done nothing to the data. It is nature. It's in its most like regular form, right? When you translate it to another like distribution, you're inherently adding the entropy of that distribution plus the data itself and its entropy. So it would definitely be less, or there will always be more entropy from that translation. That also makes the assumption that your observation is the most efficient encoding. So yeah. So when you introduce a different distribution, that's already making the assumption that distribution is not the most efficient representation of your data. I don't actually really, I think I understand intuitively, but I mean, from a math standpoint, but I'm not sure if I intuitively understand. This is basically saying that if the probability was 1 over k, and you see how like the equation above is the sum of 1 over k, like the sum of pi log of 1 over pi. So you would just have the sum of 1 over k, right? So that'd just be the log of k times 1 over k. So that would,
which is 1.
Yeah. So that's saying that the log of k would be less than or equal to, or it would be greater than or equal to the entropy of the system. So I'm not
for some k.
For some k, yeah, a very specific 1 over k. All right, for that ratio. And then the further p is from uniform, the lower the entropy. Again, this is that example that the more things are really uncertain near the mean or the expectation for that data, and then variance itself is a good variance directly correlates to information gained. So the higher your variance is, or inversely proportional. So the more information you gain, the further away you are from the mean. So that would mean that your variance would be very high, right? Right.
Yeah, because low entropy means more certainty.
Exactly. Yeah. Cool. So let's talk about conditional entropy mutual information. So this is the stuff that these examples make quite help everything make a lot of sense, like these theoretical concepts. So let's work through this example. So they have a temperature versus humidity table. So what they've done is the first bullet point represents H of T, which is the entropy of the temperature. So what you're doing is taking the entropy of uh, all cold temperatures, all mild temperatures, and all hot temperatures, or the sum of all of these. So so humidity is what's being like held constant, right? So you've got 0.3, which is just the sum. It's all of cold temperature, where across all humidities. So you have 0.1 plus 0.2, and that gives you 0.3. And then you have mild across mild low and then mild high. So 0.1 plus 0.2, or 0.4 plus 0.1 is 0.5. And then you've got hot across low and high. So that would be 0.1 plus 0.1, which gives you 0.2. And so those represent the probabilities. These are your p's. So the equation is like you saw the equation above showed it's the sum of pi times the log of 1 over pi.
Mhm.
That's
Usually log base
it's
2.
log base 2.
Okay.
Yeah. Everything here is log base 2.
Oh, okay.
So I guess we were wrong. It doesn't have to be
It doesn't have to be 1
yeah,
or
it doesn't.
less than 1.
Yeah.
Yeah. So so here all you're doing is you're taking the sum of the entropy of H of 0.3 plus H of 0.2 plus H of 0.2 or 0.5 and summing them. So that gives you 1.4. H of M, so the H of humidity would be the humidity that you experience across all low temperatures. I mean, low humidity versus and high humidity, right?
Mhm.
So for low across all the temperatures, you get 0.6. And then for high, when you add all the different temperatures across, you get 0.4. So you see that it's 0.97. And so they do the sum of H of T plus H of M to get the total entropy of the event space.
Mhm.
So that's 2.45. So joint entropy is actually so joint entropy is very similar to joint distributions, like distribution probabilities. And I think it's actually built upon that concept. So here you got like the H of T comma M is going to be the sum of the individual events. So so it's the joint space is the total observed events within that space for T and M.
Mhm.
So you can see that it's the sum of T and M. You got the probability of T equals T and the probability of M equals M times the 1 over log of those probabilities, right?
Mhm.
And so you can see H of 0.1, 0.4, 0.1, 0.2, 0.1, 0.1. And if you look at the entropy, the joint entropy of that system is less than the sum of H of T plus H of M. And that's actually really important. Do you understand why that makes sense?
Mm,
Okay, so it all goes back to the fact that the more uncommon your event space is, the more information you get out of it, right? And if you have more information, you have less entropy. So what it's saying is that you observing this specific set of numbers, 0.1, 0.4, 0.1, 0.2, 0.1, 0.1, that total event space there are more data points. I guess it's not that there are more data points,
it's
but
like
it's very specific. You got that specific ordering of data points. And so what that would mean is that for you, this event like this, uh, because it's more specific, it's a less likely to have occurred event. So as a result, you actually know more information about your future events, and that would be less than the averages of these like the individual entropies, right? Because you only took you're taking, it's not an average per
yeah, it's
se,
like
but like H of T is like
marginal distribution.
yeah. So even if you sum the individual entropies of one specific variable versus, and then sum the two separate variables together, your joint distribution is a more specific set of events to have occurred. As a result, you'll have less entropy than the total sum of those individually.
Yeah. I think another way, can you guys hear me okay?
Yeah.
Okay. Another way to think of it is that you sort of now get you sort of now have a better idea of the relationship between the temperature and humidity by taking the joint probability, basically, right? Because you're using joint probabilities as your input to this calculation. So by taking the joint probability, you have more information about how temperature affects humidity and vice versa. And
Exactly.
so
Right.
lower entropy.
Yeah.
Right. Because they're not independently, like there's some crossover in terms of how temperature relative and humidity are related.
Exactly. And that leads us into our next piece of information, mutual information. Or I guess we'll talk about conditional entropy first, but yeah, so conditional entropy is the same as conditional probability. You're doing the exact same calculation. You're taking you're trying to find the entropy of T, the temperature, given that the humidity is low. So all you're doing is you're looking at the individual probabilities of all temperatures when the humidity is low. So this is all pretty straightforward. Does it make sense?
Um,
The calculation is identical as finding the entropy. So it's just the sum of h of 1/6, the sum of h of 4/6, the sum of h, or the sum of all of those together. You're just taking p, which is 1/6, times log base
okay.
2 of 1 over, or the log base 2 of 1/6.
So you just constrain to low and then you see, yeah, okay.
Yep, exactly. Average conditional entropy. This one is the same, or this one's not the same, but this is basically taking the concept of you take the probability of uh, the temperature given that m would be low. So that is 0.6, which I think is
No, it's not 0.6. They're multiplying it by 0.6.
right. Yeah. No, I'm saying like the probability, the value of 0.6 is the probability of getting
Oh,
uh, I
M
think
low.
yeah, getting low, right?
Yeah, that was in the last slide, I think. Yeah.
And then yeah, it's this value right here, 0.6. It's this one. Oh, I can't highlight. But you see it. It's like if you
Mm-hmm.
go across the row of low, you get a 0.6 over here. So
Mm-hmm.
they're taking, it's like if the temperature, they're looking at the sum of all temperatures across low humidity. And then down here, you're taking the conditional entropy for that same thing. So that's the probability for it. And then the 0.4, which is uh, the probability that your humidity is high across all temperatures.
Okay, wait, let's think about this for a little bit. So average conditional entropy.
Yeah, so it's taking the average entropy across the average entropy of the temperature given that given the humidity. So you're taking the average of low and high together.
Okay.
So
Okay.
you see, yeah, you see how that's the case.
Yeah.
Yeah. Okay, conditional entropy. This all so there's a really useful diagram below that makes a lot of sense. This is more of the same type of calculations. You're constraining the temperature to be cold and looking at all of the humidity values for that.
Mm-hmm.
So you have you're constraining to be the temperature to be cold. So you can see that when you have low humidity, it's 1/3. When you have high humidity, it's 2/3, and then you just do the calculation. So this is how that example makes sense. And we're doing the same exact the conditional entropy again. It's the same thing as the example above. So if we're good here, I'll keep moving. Okay, so we've been talking about discrete events, like thus far. But if you have a continuous distribution, you just got to take the integral of the same equation. All right, so we're quantifying the uncertainty in y after seeing feature x. So this is that concept I was talking about. Your event space x of like your feature x of I. You have a data set of data points that fall in that under that feature, and you're calculating your uncertainty, which is the distribution that you might be mapping it to. So the entropy is always the expected number of bits needed to encode a randomly drawn value of y. So this is all just kind of going over the same exact thing that we were doing for discrete, but as for continuous. Does this make sense, right?
Yeah, I think so.
Yeah, because we're not doing anything different. We're just taking the integral over a continuous distribution.
Mm-hmm.
Okay, cool. So mutual information. So we were talking about how you have two different types of events. Like, so in temperature and humidity, you could calculate the information of you could calculate the entropy of the temperature, and you could also calculate the entropy of the uh, humidity, right? So the mutual information is actually the overlap between the two different variables. So the more you can reduce entropy, the more informative a feature is. So that's pretty much right in line with what we were talking um, about how events that are more unlikely tend to be much more informative than frequently occurring events. So they're just telling you that it's symmetric. Yeah, we'll keep moving. So here's a derivation for how they get the equation. So you have the entropy of x minus the entropy of x given y, and it basically all boils down to the joint probability of x and y times the log of the joint probability divided by the individual probability. So this reminds you of Bayes' rule, I believe.
Mm-hmm. Like something close to that.
Yeah, it's kind of close. Yeah,
Can,
I have,
can,
I have another point later.
could
When we talk
you could you um could you just talk about the information equation again? So it's you're removing the entropy of x given y, and you're just looking at basically the information. Well, you're sort of looking at the weight of x, kind of. Is that kind of what we're getting at? Like the
yeah.
weight of
So
the x
okay.
information?
So information, one of the properties of information is that, or information theory is that information of two random variables is symmetric. So what you could do is, that the entropy of h of x minus h of x given y is the same as h of y minus h of y given x. So what that says is that there is an error approaching the problem from those two sides. There will be a point where they overlap. There will be mutual information contained between those two approaches.
Uh-huh.
So
I see.
this will clear it up down here. The
Mhm.
visual illustration gives you everything you need to know to really get it. So h of x, the joint entropy between x and y is the total amount of entropy of the whole system,
Okay.
right? And what we're doing is that we can represent that as h of x times, or what we're doing here is h of x minus h of y given x, right? That's
Mm,
what we did up
can we
here.
do x given y?
Yeah, it's x given y. Oh, and here it's showing y given x. But you know that that's symmetric, so you could also do h of x given y times h of y. Here you're seeing that h, so you can see how where the mutual information is contained as the overlap between the entropy of the individual independent
Uh,
variable x and the entropy of the individual or independent variable y.
let me see.
These are plus, though, right? It's not times. Right?
Yeah, it's a subtraction, right?
No, yeah.
Yeah,
So h of x, if I'm looking at the first picture, h
yeah.
of x plus h of y, given that you know x, is the whole space, the whole entropy.
H of x
So the
given,
entropy of
or h of
x,
x minus, or h of x plus h of y given x is the whole
entropy.
entropy of the system.
That makes sense because h
That's
of
the
x,
definition of the joint distribution of entropy, right?
yeah, okay.
Yeah, and so what we're doing is figuring out, like, okay, let's calculate the total amount of entropy for our first variable, just x. And then let's also calculate the total amount of entropy of y. And then when we take the subtraction of the two, we'll be left over with mutual information.
Hmm.
So it's effectively redundant information between the two variables.
Yeah,
However,
okay, I got you.
yeah,
There's some redundant information, and you're subtracting it, and then you get the mutual information.
yeah, you're getting the mutual information. But what that means is that what you're left over with from x is the unique information that you gain from knowing x. And so that's what h of x, the entropy of x given y is.
Hmm.
At least when you're looking just at h of x.
Hmm.
I think let me go back up. Yeah. So check it out. So this right here tells you, the very first line says the information of x given y, or the x of x and y, h of x minus h of x given y. So if we go down to the bottom, here's h of x, right? Then we have h of x given y. If you subtracted h of x, or if you take h of x and subtracted h of x given y from it, you're left with the mutual information. That's the first line.
Hmm.
Yeah. So anyways, so yeah, the visual illustration of how everything breaks down helps make this a lot, like, make more sense, right?
Yeah, certainly.
I was
Cool.
just
So
doing the math and the derivation I didn't follow.
wait, yeah, go back. We can go back. What part?
It might not be important, but like going from step 2 to step 3, like I'm not sure how they were able to get rid of the summation of the probability of x. And the way they, like, that just is bizarre to me.
2 to 3.
Yeah,
On this slide, right?
yeah.
Okay. Let's see what they did.
It might not be important. It might just be it might be more important just to know and like, just because I know my log rules doesn't mean I can't understand this, right? Oh, actually, I see. I think I see it.
Can you explain it? 'Cause-
So if you take the minus and you throw it into the right side, so it's a plus, and then you use the log rule. So
But what about the py and px and pxy?
so
Oh, you did. Oh, go ahead. Go ahead. Go ahead.
Yeah, I think you're moving that entire thing over to the right side. No, you're not. No, you're not.
yeah, I guess. So
I see
then
the logs. I think I can see the logs. Um, maybe.
yeah, but the summation is the way you got rid of the way we got rid of the summation of p of x.
It might just be. It might actually be some mathematical magic.
Yeah,
I think the understanding is that because you're doing the joint distribution of x comma y, you already will go all over all x's as as a part of that sum. So
count.
Mhm.
you might be able to just turn that into a singular thing, go over x's and y's, but you need to uh, bring in the p of x
That makes sense.
in that section.
Mhm.
I think that's how you end up with the division, because you take the p of x that you had in the first line and you end up dividing it.
Well, I thought that's when you multiply those logs together.
No, you're right. It is when you multiply the log together.
So I don't know what happens to, maybe it's part of the math magic you talked about, but this is splitting hairs. It's probably not important.
Okay, let's keep going. Okay, so we're going to talk about cross entropy. So cross entropy is really important, especially in cluster evaluation, because I guess the idea behind cross entropy is how many bits are you wrong by uh, when you assume a distribution. So this is the case where we're talking about, I've got I got a set of data points, and I am going to assume a distribution Q, and this is going to tell me the entropy between that assumption. So between my actual observed data and the distribution I'm trying to model it by. And cross entropy has a direct cross entropy loss is a evaluation metric, and it actually is the equivalent of maximizing the log likelihood of a data point. And we'll look like the derivation will be a little more clear. But so what they've done here is that you can see the first line, the entropy of P comma Q, or the joint distribution of, the joint entropy of P and Q is the negative sum of the probability of X, I guess the probability distribution times the log of Q. And that is also equal to the entropy of P by itself plus the Kullback-Leibler distance of P and Q. So we'll talk about that part later, but the most important part is here and highlighted in green. Yeah, so that's really the most important part. And honestly, there are very few times where you'll be calculating this by hand because it's a core metric. It's like a core package feature in PyTorch and TensorFlow and Keras. So you won't need it, but it is a measure of how many bits it will cost you to be wrong about your assumption of that second distribution. Everything here is about taking observed data points, so your data that you will have observed to be, and then trying to fit distributions that make the most sense. So the least wrong distribution.
Is it least wrong, or is it minimizing the bits we're sending?
It's the same thing. So being least wrong is the same as minimizing your entropy, which would maximize your distribution matching your data points.
Okay, I see.
Yeah, it's the same as like, say I have a set of labels. So I have data points and I have labels, and the labels are my truths. And my system, my probability distribution, or not probability distribution, but my distribution Q is what I assume the distribution to be. So you can calculate how wrong you are between the two by using probabilities, like using this entropy, cross entropy. So if you see like the joint distribution between, or the joint entropy of P and Q is the expectation of P given the log of 1 over Q of that data point. So 1 over Q, so the new distribution that you're assuming, and then the observed data point you're looking at.
So Li represents the observed.
Li is representing your translation.
Okay, thank you.
Yeah. So I can have 10 coins, and I have a data set of I flipped the 10 coins and I recorded their outcomes, and Li would be the translation of taking the probabilities from that observed set and whatever I predict my new distribution Q to model it as.
Okay.
Yeah, and so you'll end up with this at the bottom. It's the negative sum of the probability of X occurring, and then times the log of Q of X. So this makes sense intuitively.
I think I see the math, but I still don't get why Li is equal to log of 1 over Qi.
I don't actually know what Li is specifically labeled, like what the name of Li is, because I think it might just be an intermediary variable. But the concept is that you're trying to calculate the expectation of your data point of the new distribution. So I guess that concept is the, I think that concept is what's holding you guys back a little bit.
Yeah. Okay.
No, go for it.
I think Li is the minimum length of information, or the optimal length of information needed to describe your new distribution Q. I think it has less to do with the actual distribution and more to do with the amount of the information needed to describe it, where L represents the length.
How does that give you log of 1 over Qi?
They derive it in one of the readings, because basically the optimal length of information used to send is related to the probability of something happening. So I think that's your Q of X. We can't hear you now.
Okay, I think you're back to normal.
Okay, I was saying real quick before we move on, just real quick, sentence definition of Li. Or that log thing.
Oh, yeah. So I'm not,
one sentence.
yeah, I'm not sure if, like, I'm not sure if it's the length or not, but it's a measure of the, like, correlation isn't the right word. I guess
I vaguely remember from the article, because I mean I read it like when we were going to do the first lecture, because we were supposed to do it for this, but and so I haven't read it again, but I sort of vaguely remember representing like sort of what you can represent, I guess, with this log of. Okay, so actually it's fine. I can just go read it. Yeah.
I think the shitty part is that the framework that the article uses is very different from the framework that the lecture is approaching this, and that's why like they don't directly talk to each other.
I can send you guys a link to an article that explains cross entropy really well, and actually does examples, so it'll make a lot of sense. So effectively, like, all of this is just to say that you're trying to turn your observations of your data set P into knowledge. And in order to do that, you need a distribution or a model Q, right? Because what you have right now is a discrete set of points,
Mhm.
you know, and so you need a distribution to represent that. And that's what Q is.
Okay.
And we looked at what the definition of entropy was, is if it was all discrete, it would just be the probability of P times the log of P of X, remember?
Mhm.
So what this is saying is take the probabilities from your discrete distribution and then insert those into the log of Q of that.
Mm-hmm.
Yeah. And so this is trying to correlate how good is the probabilities, like your probabilities from your observations are the truth. No one's changed that. So you're taking those probabilities and seeing how well that Q maps to those probabilities. So how well does it function as a modeler? And basically, the higher the entropy is for that, the worse of a model it is.
Okay, that makes sense.
Yeah, and so that's what the cross entropy is between. You're seeing the difference.
Mm-hmm.
Actually, the Kullback-Leibler divergence actually is a distance measurement between those distributions. So we can look at that. I've never actually used this like specifically, but I've read a little bit about it and how it plays a part in deciding where the lines of, like, if you mapped all your data points onto a graph and you had to figure out how do I split my graph, this distance is actually one of the is a useful measure of how to split your data. So it measures the theoretic quantity between two distributions, and it calculates excess bits. So here you've got like two. So the distance itself is like the cross entropy. Yeah, okay, it's the cross entropy minus the entropy of P itself, like by itself.
Yeah.
So it's kind of the same as not mutual information. It's like the reverse of it. You're basically subtracting out the entropy of the joints, like the entropy of just P, and you're left with what's the overlap, and that's what the distance is. Does that make sense?
Mm-hmm.
Difference between two distributions.
Yeah. So like, think about it like in a graph. If I take my 10 coin flips and I have my new distribution Q and I throw my 10 coin flips in those X values into the new Q and then actually graphed both sets of discrete data points, my q of x of I and my p of x of I. This is the distance, the physical, like the actual distance between those two on graphs, those two data points. So I have a p of x of I and I have a q of x of I, and I've figured out what the distance is between them if I mapped them out physically. And by distance, it means like how different are they in terms of bits? Because all of this is just to say like it's all about entropy, so it's all like calculating information, right? So it's not necessarily like this thing is actually three units away from whatever. It's not. It's saying that if the entropy, I guess it's saying that like, okay, there could be, it takes me 3 bits to represent p, and for q it takes 6 bits to represent q. And so now I'm calculating what the excess of that mapping is.
Yep.
Cool. So that's that. I'm gonna kind of gloss over the math here because it's not that important. I mean, you guys can go through it like specifically, but it doesn't come up that often.
Sure.
Yeah. So this is the summary. So cool. So yeah. So we talked about entropy. We talked about what optimal encoding actually is, like what actually means. We talked about joint entropy, conditional entropy, mutual information. We talked about the intuitions, relationships, and then cross entropy, and then Kolbach-Liebler. And cool. So this actually was a good lecture to pair together with cluster evaluation because a lot of the ideas here naturally translate over there. So I'm gonna go ahead and stop. Actually, maybe I don't have to stop sharing.
I think you should stop recording and then go ahead and record the other one.
Oh,
okay,
do you want to
I can do that.
Recordings?
Yeah, it's useful.
You think it's useful to stop and then do another one?
Yeah, because I could foresee myself doing the homework and.
Oh, okay. That's fine too.